Concept of solution. Suppose we have a function y equals to f of x that is a solution of some ordinary differential equation given by f of x, y and y prime equals to 0 on some open interval x lying between a and b. Then the differential equation becomes an identity, meaning that the equation is true for all values of x in the given interval if y and y prime are replaced with f and f prime respectively. Let's understand this with the help of an example. Let y be equals to c over x, where c is an arbitrary constant, is a solution of the differential equation x times derivative of y with respect to x equals negative y for all values of x not equals to 0. So here we have y equals to c over x. So c over x is a function of x. Now we differentiate it with respect to x. That gives us y prime is equals to negative c over x squared, where negative 1 over x squared is the derivative of the function 1 over x, and that is f prime of x. Now the ordinary differential equation x y prime equals to negative y is an identity if x f prime is equals to negative f, where we have replaced y prime with f prime and y with f. That is x times negative c over x squared is equals to negative c over x. The x and x get cancelled out. That leaves with negative c over x equals to negative c over x, which is true. Because this differential equation consists of an arbitrary constant c, we have a general solution of the ordinary differential equation. Note, we'll later see that c is not arbitrary. Sometimes it needs to be limited to a certain interval. This is done in order to prevent the need for complicated expressions in the solution. We will be creating techniques that provide specialized answers to general problems. Thus, we will then say the general solution of a given ordinary differential equation instead of a general solution. Geometrically speaking, the general solution of an ordinary differential equation is a family of many solution curves, one for each values of the constant c. When we choose a specific value for c, we obtain what is called a particular solution of the ordinary differential equation. There are no arbitrary constants present in a particular solution. Initial value problem. In most circumstances, a particular solution is obtained from a general solution. By using initial conditions, y of x0 is equals to y0 with given values x0 and y0, the values of the arbitrary constant c can be determined. Geometrically, it means that a solution curve must pass through the point x0, y0 in the xy plane. Whenever we have an ordinary differential equation and some initial condition, we have an initial value problem, or IVP in short. As a result, if the ordinary differential equation is explicit, that is, y prime is equals to f of x comma y, then the initial value problem is of the form y prime is equals to function of x and y, where y of x0 is equals to y0. Let us consider an example. The ordinary differential equation x times y prime is equals to negative y, with y of 1 equals to 2, representing an initial value problem as the general solution y is equals to c over x. Using the initial value y of 1 equals to 2, that is when x equals to 1, then y equals to 2, we get 2 equals to c over 1. Solving for c, we get 2. Such that y equals to 2 over x becomes the particular solution for the initial value problem x times y prime is equals to negative y, for y of 1 is equals to 2. Worked out problem number 1. Verify that y is a solution of the ordinary differential equation y prime equals to sin x plus cosine of x, with y equals to sin x minus cosine of x and the initial value y of 0 equals to negative 1. Here we have the differential equation given by y prime equals to sin of x plus cosine of x with y of 0 equals to negative 1, equation number 1, that represents an initial value problem. Now using y equals to sin x minus cosine of x and differentiating it on both sides with respect to x to get y prime equals to derivative of sin x will be cosine of x plus derivative of negative cosine of x will be negative sine x, so we have plus sine of x, which satisfies the differential equation. Also, using the initial condition, when x is equals to 0, we get y of 0 will be equals to sine of 0 minus cosine of 0. Here we have replaced x with 0, so that gives us negative 1. So indeed, y equals to sine x minus cosine of x is a solution of the initial value problem. Y prime equals to sine x plus cosine of x with y of 0 equals to negative 1. Problem number 2. Verify that y is a solution of the ordinary differential equation y triple prime equals to 0 with y equals to x squared plus 2x plus 1 with the first initial value y of 0 equals to 1, the second initial condition y prime of 0 equals to 2, and the third initial condition y double prime of 0 is equals to 2. So here we have y equals to x squared plus 2x plus 1. Let this be equation number 1. And we're going to differentiate 1 with respect to x, which should give us y prime equals to 2x plus 2. Let this be equation number 2. Differentiating 2 with respect to x, we get second derivative of y equals to 2. This is equation number 3. Differentiating equation number 3 with respect to x, we obtain y triple prime equals to 0. Thus, y equals to x squared plus 2x plus 1 satisfies the ordinary differential equation y triple prime equals to 0. Also, from equation number 1, if we replace x with the value 0, then we have y of 0 equals to 0 squared plus 2 times 0 plus 1, which gives us 1. So this satisfies the first initial condition. Now going to equation number 2 and substitute x with 0, we have y prime of 0 is equals to 2 times 0 plus 2, which is equals to 2. And finally, from equation number 3, we have second derivative of y calculated at x equals to 0 also gives us 2, and this satisfies the third initial condition. Hence, y equals to x squared plus 2x plus 1 is a solution of the initial value problem.